All right, so today's lesson is about how the normal force changes at various points in a vertical circle. And ultimately, we're going to see why we could twirl that glass without having, the glass fall down. And of course, you could try this at home with just a regular pail of water. You could take a regular pail of water and you could twirl, and you could take it and get it going, and you could twirl the pail vertically, and the water will not fall out. But of course, you have to be twirling it kind of fast, because if you took the pail and you went up slowly, the water would just fall on your head. Okay? But if you're going fast enough, the water stays right in the pail. So we're going to look at this question here. How does the normal force change at various points on the vertical circle? And then ultimately answer the question, why does the water stay in the pail? You ready to roll? Okay, so we're going to draw a free body diagram. Each case, okay. So we're going to let the radius be 1 meter, and the mass is going to be 0.1 kilogram, and the velocity is going to be 6 meters per second.
No, it's m times ac.
Okay. All right. So there's more notes for me than you. Okay. All right. So here we have the twirly platform, the glass of water sitting on the platform, and there was no tape or anything special. It's a very smooth piece of whiteboard that just got cut down in the glass, just was set right on there, and basically, we're going to consider various points where the glass is at, and right now we're going to do this one first, and then let's see, then we're going to consider it when it's here, and then we're going to consider it when it's up there. So basically, what we're going to do in each case is we're going to use that initial data over here, and we're going to solve for the normal force. Okay. So case number 1 here. If you wanted to draw a free body diagram acting on that glass of water, free body diagram shows all the forces acting on the water at that particular point in time. Well, at this particular point in time, you have the weight force pulling it down, but the platform underneath the glass is pushing up on the bottom of the glass, and that's that upward normal force. So you have the downward weight force, and you have the upward normal force. Now, we know that the glass is going in a circular path. And if something is going in a circular path, there has to be an overall force acting which way? Which way does the overall force on that glass have to be acting if it's going in a circular path? Cindy? Towards the center. So there has to be an overall force towards the center, and we know the only 2 actual forces that are acting on the glass is the actual weight force and the normal force. So knowing that there has to be an overall effect towards the center, an overall force towards the center, which of those 2 forces has to be bigger in this case? The true weight force, or the amount of force that the platform beneath is pushing up on the glass, the normal force? Michael? The normal force is going to have to be bigger, yes? Because there has to be an overall force. So one of the main strategies in solving physics problems is drawing a free body diagram showing all the forces, and then applying law number 2 from a man named New.
Time.
ton
I didn't get my log.
to the particular point of action there. So let's go ahead and apply law number 2 here, which says that, look, the overall net force is going to equal to the mass of the object times the acceleration of the object. But in this particular case, what's going to be an expression for the net force? We know there's an overall force towards the center. So what can I rewrite net force with, Justin?
The normal? Or isn't it the difference between the normal force and the weight force?
That's it. Okay, it's the difference between the normal force and the weight force. It's going to be the normal force up, which is the bigger of the two, minus the weight force down. So the overall net force of that glass right there is going to be the resultant of the forces acting on it. And if the bigger one's going up and the smaller one's going down, it's the bigger one up minus the smaller one down. So I'm just applying law number 2 for men and new. Ton. Okay, and the net force is just going to be the normal force up minus the weight force down. And that's going to be equal to the mass times the acceleration. But however, this acceleration right here is a centripetal acceleration. It's the acceleration due to the fact that the water is going in a circular path. You guys want him to shut that window a little?
Well, she's just waving.
Just shut it halfway. There's the song. I'll meet you halfway. That's better than no way. David Cassidy, Partridge Family, 70s.
Wait, who sings that?
David Cassidy with the Partridge Family. Yes.
Oh, can I write when you could say the acceleration?
Yeah, what can we substitute in for the acceleration? Since it's a centripetal acceleration.
V squared over radius.
Exactly. V squared over R. Good job, Samantha. V squared over R. The upward normal force minus the downward weight force gives you the net force. The mass is the mass. And since this is a centripetal acceleration, because it's going in a circular path, we know the acceleration equals V squared over R. And then, of course, the weight of the glass, Fg, that could be replaced by, Justin?
M times 10.
Yes, m times g, which is eventually going to be m times 10 because we're on the surface of the Earth. So we could rewrite this one more time. The normal force minus m times g. So how much of the glass is being pushed up
Isn't V
minus the weight coming down equals mv squared over r. And if we're using our given data, we basically have enough information to solve, plug in for everything and solve for what's the one thing we don't know at this point. The normal force. We can actually solve for how much is the platform below the glass actually pushing up on the glass. So what we're going to do is we're going to solve for the normal force. So we could plug in all of our variables. Normal force minus 0.1 kilogram times 10 meters per second squared. In that formula, Fg equals m times g. You plug in g as positive 10 meters per second squared. So in that formula, you don't put in a negative 10 for g. Okay? And then when you crunch that out, right there, that whole value comes out positive, and then we're subtracting it because it's down. If you put in negative 10, then, which could be done, it's, because the acceleration is downward, but then essentially then that would be a positive sign over here. The bottom line is it's the magnitude of the normal force, which is up, minus the magnitude of the weight force, which is down, and exactly. That's why when we're using this formula here, we're usually just trying to get the magnitude of the weight force, so we don't use negative 10 in that formula there. That's a great question, by the way. All right, so then we go to the right-hand side of the formula. And on the right-hand side, we're going to have, let me make some room over here. So we have, what is that going to be? 0.1 kilogram times the velocity. We're saying that we had that sucker spinning 6 meters per second squared divided by the radius, which is about 1 meter. And then we have everything except for our F sub n. And if we solve that for F sub n, what do we end up getting? Did anyone crunch that out? Samantha? 4.6 newtons? And if we take a quick look at the weight of the object, if we took a quick look at the weight of the glass, yes, the weight is that m times g, which is this term right here. How much does the glass actually weigh? 1 newton. So the glass of water is about 1 newton, yes? So F sub g is 1 newton, but the normal force pushing up on the glass is not 1 newton. It's more than 1 newton. If the normal force pushing up on the glass was equal to the weight force, then the glass would have to be going off straight like that, not going up or down vertically. But the glass doesn't continue just to go like that. The glass ends up rising up. So we know that that normal force up has to be bigger than the weight force down.
Wait, and the velocity is the tangential velocity, right?
Correct. Exactly. That velocity is the tangential. So if you want to be a formula memorizer, okay, you need to know with vertical circles, when you're considering the point at the bottom, law number 2, which starts off looking like this, ends up looking like this. I myself just draw the free body diagram, write out law number 2, and then see, what forces are actually pulling it towards the center? It's Fn minus Fg. We ready to move on to the next case? Okay. Ching. Ching. So at this point, we want to draw all the forces acting on the glass once again. And we have the weight force acting down, F sub g. And we have the platform underneath the glass pushing up on the bottom of the glass, which is the normal force. And we know, since the glass is going in a circular path, we know there has to be an overall force acting in which direction? Anytime something goes in a circle, there has to be a force on the object acting in which direction? Risa?
Towards the center.
Towards the center. Now the tricky thing is, what is actually providing the centripetal force? Last time, both the force of gravity and the normal force played a role in determining the centripetal force. But this time, when we go and we write down law number 2, we only want to consider the forces acting towards the center. Let's just finish this up and then we'll take a break. If we're going to consider the forces acting on the center, this formula here becomes the centripetal force equals the mass times the centripetal acceleration. But what force is providing? Let's put it this way. Which force is solely providing the centripetal force this time? Rishad? F sub n. The normal force, that platform pushing in this way, is providing all of the centripetal force. The force due to gravity, which is acting vertically, is in no way, shape, or form helping out or hindering that horizontal centripetal force.
Oh, wait.
So in this particular case, the centripetal force simply becomes the normal force. And that's going to equal m times v squared over r. The force due to gravity, which is perpendicular. Remember, perpendicular vectors are independent. Well, that perpendicular force due to gravity in no way, shape, or form helps push that glass towards the center of the circle. Comment, Justin?
Yeah, when it's vertical, it works concurrently with it, right?
Exactly. And that's the next slide. Good foresight. Take a break, guys, and come back. We'll continue in a moment.
I have to go with my health teacher to talk to Dr. Durante, so I'll be back like a couple minutes in the period. She's going to give me a pass to come back. But just telling you.
Okay.
I'll be right back.
On my quiz, like, I thought you said.
Okay, we're back here at Showtime Slasinski, and we were considering the vertical circle motion of a glass of water being flung on a platform, and at the right-hand side, we talked about how the force due to gravity, the weight of the water, in no way, shape, or form helps push that glass towards the center, so it's not providing any of the centripetal force. So basically, in this case, it's just the normal force. So if you're a formula memorizer, at this point right here, this is the formula you have to use. And if we plug in values, what do we get for F sub n? Well, it's going to be equal to, what was that, 0.1 kilograms times 6 meters per second squared all over the radius of 1 meter. Yes? And what do we get for the normal force at this point? How much does the platform have to push in on that glass to keep it there? Michael?
0.6 newtons.
0.6 newtons?
You have to learn. 0.36. 3.6.
3.6 newtons. Notice what happened to that normal force. Compared to the bottom point, let's take a look back. At that bottom point, the platform had to push up on the bottom of the glass with a force of 4.6 newtons. Now, at the side, at the side, at the side, at the side, the platform has to push in 3.6 newtons. Okay, not as much.
feel this when he was spinning it, like it was heavier than bottom?
Yeah, you can feel that. It's also, because that also gets translated into the tension in the string. Absolutely. And then, what do you think's going to happen when we go to the highest point?
Same.
What do you think's going to happen to the magnitude of the normal force now? Justin?
It's going to be the normal force plus the force due to gravity.
That's what's going to make up the centripetal force, true. But when we solve for that and we get the normal force answer,
It'll be greater.
okay, well, look at the pattern we were looking at here, Justin. At the bottom, it was 4.6 newtons. And the normal force not only had to support the weight force, but it had to provide extra to pull it up. 4.6 newtons. And then over here, the normal force didn't have to balance out the weight force at all. All it had to do was provide the inward one, and it was a little bit less. And then when we get to that top point,
Wait, it's 0?
okay, it's going to be even smaller yet. Because the normal force isn't going to be providing all of the centripetal force. What's going to be like helping out, like a dear old friend, Julie? The weight force is going to be helping out. So it's not going to be all on the normal force. So we draw our free body diagram at that high point right there. The weight of the glass, of course, pulling it down at this point. But now, the platform below is going to be pushing the glass this way.
So now, what makes up the outwards force?
What's that?
I know there's no outwards, but like, why does the it's for inertia, right? Is that why it stays up there? Is that right?
Well, at this point, if you're going fast enough,
The inertia will carry it over.
the platform is still going to actually have to push down on the glass, because what does the glass want to do at that point? It wants to fly off tangentially that way. So this platform right here is saying, hey, 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 you're not going to fly off that way, and it ends up pushing it down this way, which makes the makes it follow that curved path. So let's apply law number 2 from a man named Newton, which says that the overall net force is equal to the mass times the acceleration. What's going to be an expression for the net force this time, Robbie?
Fn plus Ft.
That's what I'm talking about. Fn plus Fg. And that's going to equal m times v squared over r. And Fn is the thing that we don't know, plus Fg, which is m times g. And that's going to equal m times v squared over r. And now we could substitute in all of our values, and we get 0.1 kilogram times 10 meters per second squared equals 0.1 kilogram times the 6 meters per second squared all over the whatchamacallit radius of 1. Oopsie, forgot that square there, and I don't want it there, I want it there. Okay, and now when I solve that for the normal force, Julie? 2.6 newtons. Samantha?
Just like a general question, I don't understand. Are you okay? Just like something else when it's a quick, it's not like a 90-degree angle.
If it's not at a 90-degree angle, it's a pretty interesting question. Like if we consider the glass over here,
Yeah.
and we got the cup right there. We would still have the normal force pushing in on the bottom. Yes? And then we'd have the force due to gravity going this way. And that force due to gravity would have to be broken up into components. Because part of that force due to gravity would be pulling this way, and part of that Fg would be pulling that way. So this is one component of Fg, this is another perpendicular component of Fg, and if I call this one little component of Fg A, and I call this other little component of Fg B, which component of Fg is going to be contributing to the centripetal force, A or B?
No,
A, because A is going to be, that part of the weight is going to be helping the normal force push the glass towards the center. B here wouldn't be helping at all. You know, B ends up helping speed up the glass in the tangential direction. So it's definitely a doable problem. It's just that the F sub G would have to be broken up into components. Okay. Usually the popular cases are the bottom, where the net force is the normal up force minus the weight force down. Why is it funny? And then the side, where the normal force provides all of the centripetal force. And then the top, where the normal force plus the weight force provides the centripetal force. If you're a formula memorizer, here is the formula to memorize at the top. Julie.
So does the normal force decrease until it reaches the top and then increase as it goes forward?
Exactly. Exactly. Now, instead of twirling a glass on a platform, what if I had like a little tiny person riding on a bathroom scale? Okay? If I had a little tiny person riding on a bathroom scale,
have you ever done that?
Don't make fun.
okay, and here's the little bathroom scale, and the bathroom scale maybe is, you know, hung by a little rope here like this to the center, and then, you know, maybe there's a person sitting here, you know.
You're right, that's pretty bad.
Little person sitting on the bathroom scale. Okay. Remember, we talked yesterday, the reading on the bathroom scale, which also indicates how the person feels, is always indicated by one measurement. Think back to yesterday's lesson. What measurement always indicates what the bathroom scale would be reading, which is also how the guy apparently feels he weighs. Bradley?
F sub n?
F sub n, yes? So if he was riding on a bathroom scale, and we just got done talking about how F sub n is the greatest at the bottom, well then at the bottom right here, oh my god, there would be the biggest F sub n. Because not only does it have to balance out his weight force, his true weight force, it's got to add a little extra so that there's an overall upward force. So at the bottom right there, the scale would read the most, and he'd feel like, oh, no, so heavy into his seat. And then as he comes around to that top point up there, what's going to happen? If you look down between his legs and read the bathroom scale he's sitting on, what's going to happen to that bathroom scale reading on the top point?
Much less.
It's going to be much less. And whoa, I feel so light. You know? So keep in mind that the normal force is equal to the apparent weight, which is always indicated by a bathroom scale.
Wipe down the bathroom.
You could be going to the bathroom anywhere. And it happens on these rides. That's besides the point.
Is that on a roller coaster, like when you're doing like the flip, like at the top, you feel really light? At the bottom, you're like in the floor.
Oh, that was funny.
Exactly. Exactly. And we're going to look at this. So, take a look at these fill in the blanks. At the bottom point, the normal force is the smallest or greatest. At the top point, the normal force is the smallest or greatest. Junie, you want to read it nice and loud? Fill in the blanks.
At the bottom point, the normal force is the greatest. At the top point, the normal force is the smallest.
Great job. There, I filled it in for you. Okay. Fill in the blank. The normal force is always equal to the blank weight. And only one of those words can correctly be placed on the line. Ricky? The apparent weight. At which point would the rider's apparent weight be the greatest, be the least? Point A, B, C, or D. Where would the apparent weight be the greatest? Hannah?
Be the greatest at A.
Correct. And where would it be the least?
C.
Correct, at C. Okay. And if you had to explain why, the best explanation would be that at the bottom, not only does the seat have to hold up the person's weight, but they have to provide extra to keep them going in the circle. But around top, the seat doesn't have to push as much because what's helping out with that? Gravity. F sub G is helping out with the centripetal force. So the seat doesn't have to push as much. Good job, Prashant. Samantha?
So you know, like when like a snowboarder does like a flip,
Yeah.
so the reason they like stay on
You always put the same stuff on the boots.
oh.
You mean, what do you mean when they do a
Snowboard's
flip?
just strapped in. Do you mean skateboard?
No, but like you know,
Skateboarding is a better example.
yeah,
Skateboarding
skateboarding.
is
So like when they do like a flip,
Well, they hold onto the
Well,
board.
they're also holding it.
and then you know,
You know
so
enough
like,
theory.
you know, like
In theory.
Yeah.
why don't they just like fall straight?
Do you mean a
down?
half? Do you mean a half pipe? Like a full pipe?
I don't know.
Yes, full.
Like, are you thinking of a full, like, not the actual board? You're thinking of like the thing they ride in?
No.
Well, then you're wrong.
Are you asking why they, when they go like that, they're not falling?
Yeah.
They're the
Yeah,
same
that's
same
not
reason.
velocity.
Fast enough.
I mean, I get.
It's in our
Yeah, that velocity is
The same reason, like when you're at the top of the circle, you don't fall just straight down. Because when you're up here, you happen to have a really fast velocity this way. So you want to keep going that way. And eventually, if there wasn't a ride, you would fall down like this, like a projectile, yes?
Right.
All right, but you don't fall straight down this way because you have that tangential velocity. And why don't you just continue going off? Well, the ride itself says, hey, you're not going over that way. I'm going to push you inward with that normal force. And that normal force keeps pushing inward, preventing you from going the way you want to go. So anytime somebody goes through a circle like this, a vertical circle, the reason they don't just drop down, they have to be going fast enough tangentially. If a skateboarder or a roller coaster ride or that glass of water was just placed at that top point and wasn't moving tangentially, it would fall down.
So could a circular motion problem turn into a projectile motion problem?
Sure.
Like, are we in questions like that? Could we?
I've seen it. So this time, the normal force is replaced by a tension force. If you're swinging that weight around in a vertical circle, there is no like platform below, like pushing up on the bottom of the weight. There's only these string attached, yes? So in this case, you could think of the normal force as being replaced by a tension force in the string. And even when I was whipping that glass of water around in a vertical circle, I felt that tension in the string as well. So at what point would the tension be the greatest? And at what point would the tension be the least? Good job, hands that are always going up, trying to keep everybody into this. Miss Jessica, where do you think the tension force would be the greatest? Point A at the bottom. That's where the rope has to pull up the most. Because not only is it supporting the object's weight, but it's got to pull up extra to keep the object going in a circular path. And where would that tension force be the least, Jessica? Point C at the top. Okay, I don't have that set up. Okay. So, now what we want to do is calculate how slow can you go? Because obviously, if I'm spinning fast, we're sure that the glass is going to stay in there. But if I start going slow,
Yeah, I'm moving at a compass.
that's the question. How did this thing get switched around?
Top.
So if I put this right here, see how slow I could go. So
Why would you?
going fast is not a problem. But slow. Whoa! Everybody okay?
I saw that.
Plastic cup.
Yeah, it's plastic, guys. Come on, you think I really use glass? Oh my god.
Yeah, I thought it was glass.
Yeah, I thought it was glass for a second.
Alright.
Let's try again.
Everybody okay here? Front row?
Splash zone. You did that on purpose?
No.
Well, I did go slow, and the slower you go, the bigger the risk. So, we're going to,
Same applies to driving, right?
we're going to look at that top case with ever decreasing velocities.
You probably have, so. I mean, I know who this is saying, so.
Yeah, Mr. S is a fan of salt that
Yeah.
I have to go buy sandwich.
Every time I hear it,
There's no better idea. I'm wearing a sandwich.
Okay, so, yes.
Question. So, for points, let's just using the last diagram as an example. For points B and D, is the F sub n always equal for them?
The normal force would be the same on both sides. Yep. Point B and point D would have the same normal force. Yep. And in this case, it's the same tension. Great question.
Oh wait, don't.
Okay, so what we're going to do, folks, is we're going to recalculate this a few different times, and basically what we're going to do is we know that at that top point right there, the weight force is pulling the glass down, and the normal force, the platform, is pushing on the bottom of the cup this way. And we know that, well, number 2 says that the net force is equal to the mass times the acceleration. So, in this case, both the normal force down and the weight of the object down equals the mass times acceleration. Acceleration is equal to v squared over r, and then we have the normal force plus n times g equals mv squared over r. So what we're going to do is we're going to look at the hidden relationship between the tangential velocity and the normal force. So we're trying to establish what is the hidden relationship between the tangential velocity and the normal force. As that velocity decreases and gets smaller and smaller and smaller, what happens to the amount that the platform below has to push down on that? You can make your hypothesis in your head. Now what we're going to do is, we know that the normal force plus 0.1 kilogram times 10 meters per second squared equals 0.1 kilogram times the velocity squared over 1 meter. And we'll break this up, folks. We already calculate when the velocity was 6 meters per second. What did the normal force turn out to be from the top point? We did that before. What was it? Was it 3.6 or 2.6? 2.6. So let's say we weren't spinning it fast. Let's say we were spinning it at 5 meters per second. What would the normal force come out to be? And then what if we were spinning it at 4 meters per second? What would that normal force be? So why don't I split the class right down the middle here. You guys over here, if you don't mind, you could calculate the 5 meters per second. You guys over here, you can figure out the 4 meters per second. Let's see what's going to happen to that normal force as we slow it down. Let's slow it down. I'm trying to be like a record slowing down. Did you get to the 5? Okay, what did the normal, Junior, what did it come out to be when the velocity was 5 meters per second? 1.5? Okay, and Mike, what was it when it was 4 meters per second?
6.
And if we went down to 3 meters per second, guess what would happen to the normal force? It'd be even less, yes? And the question is, how slow can we go and still keep that glass of water on the circular path? Justin?
I think up until when the normal force is equal to the force due to gravity.
You're so close, but you got to tweak your thinking a little bit. Look what the normal force is doing here. All right, the normal force here, if it's 6, is 2.6.
1 is 0.
Right, right. Eventually, we want to figure out when the normal force is 0, because when the normal force is 0, okay, what will be providing all of that downward centripetal force at that top point? The force due to gravity. If you go slower than that, then the force of gravity will be bigger than the required centripetal force, and the force of gravity will just make it fall straight down. So if you want to find out how slow you can go, you go back to this formula right here. You consider the top point. And you let that normal force be 0. So, Honda, did you work that out?
Oh, no, I was gonna, never mind. I had a different question, but I just answered it.
Okay. Did anyone do that calculation backwards? Anybody on it?
Yeah.
Risa.
You want it like decimal?
What do you got?
Well, rad 10, which is like 3.16.
So I'll say 3.2 meters per second.
Solve for B.
Okay.
And equal to.
If you went slower than that, what would the normal force come out to be? Negative. And that means like the normal force, instead of acting down, would have to act up to hold the glass there, because what would it want to do? Fall down. You know what I mean?
That's not possible, right?
Well, you'd have to crazy glue the cup to the thing.
Sure.
You know, the normal force, instead of pushing down, would have to be like grabbing the glass bottom and holding up. Okay. So, let's see what we got here. How slow can you go?
There's a song that goes like that, except it's slow, not slow. But you can make it slow.
All right,
And
I'm
you
gonna
can
look for
sing it to
that.
your classes now.
Mindy listens
It's
to
called How Low Can You Go?
Yeah.
Wait, 3 points is like sort of, I wonder if it's the point where, is that like the limit, or is that the point where it falls?
No, that's the limit. That it'll just stay still on the circle there, because at the top point the normal force would be 0, but the weight force is exactly how much is required to keep it on the circular path. Okay, so that's the limit. It still just works at that point. So as the velocity decreases, the normal force decreases. How can the velocity be calculated? That would finally make the normal force equal to 0. What will happen if the velocity is any slower? The glass will fall. The glass will free fall. Water will go everywhere. There will be a big mess. That's what happened here.
And our test
Yeah,
is that.
people be careful.
Oh yeah, Reese, you missed it.
What?
You missed it.
I saw it.
So to determine how slow we can go, consider the top point of the circle and let Fn equal 0 and solve for the velocity. Or another way of thinking about it, if the normal force is equal to 0, then essentially what's going to be providing all this centripetal force? Force due to gravity. Or simply let the F sub c be equal to the weight of the object. and solve for V. Or,
Isn't that really just like,
It is just making it zero, because
Yeah,
zero,
that's why I
one is
just-
something.
Exactly,
so
exactly.
something.
or another way of thinking about it, if the weight force is equal to m times g, then if you want to solve for how slow you can go, essentially, the centripetal acceleration at that top point of the circle has to be equal to the acceleration due to gravity, g. See how the m's cancel out? If it's going so slow that the v squared over r is less than g, it'll fall. Or simply let the centripetal acceleration be equal to g, which is 10 meters per second squared on the surface of the Earth. Okay? Multiple choice question. For the glass of water demo, for the glass of water to make it through the vertical circle, the velocity has to be fast enough so that the A, required normal force, is greater than or equal to 0. B, the required centripetal force is greater than or equal to F sub g. C, the required centripetal acceleration is greater than or equal to g. D, all of the above. Survey says, Cindy? D, all of the above. You know, there's 3 different ways of thinking about it. Sure. Ready, Freddie? So, somebody walks up to you and says, hey, why doesn't the water fall on the glass at the top point of the circle? What would you say? Hannah?
Because the acceleration is greater than gravity? Like, that's like
That's an excellent answer. The centripetal acceleration required to keep it in a circle is greater than the acceleration due to gravity. So, if it's going in a circle like that, and the required centripetal acceleration at the top point is greater than the acceleration due to gravity, it'll stay there. So, great answer.
Wait, does that make sense?
What's that?
You have we just said that the centripetal acceleration. Oh wait,
It's actual centripetal acceleration, the v squared over r,
never mind, I'm sorry.
has to be greater than or equal to the acceleration due to gravity. Does anyone else want to answer it a different way? You know, how would you answer your friend? Like, I don't really get it. Why does the water stay in there? Mike?
the normal force greater than 0.
The normal force is greater than 0. That's also 100% true. Okay. I ended up saying this. Let's see what I say. At the top point, the downward force required to keep the glass of water traveling in a circle is greater than the weight of the glass of water. Actually, you know what it should say there? That's a little bit of a... It should say is equal to or greater than the weight of the glass of water. Or sometimes if I'm trying to explain this to somebody else, I'll simply say, hey, look, at the top point, the water is moving so fast tangentially, like that way, that it doesn't have enough time to drop out of the glass.
That's true. That's a good point.
Well said.
Wait, so what lessons should we do? 7 and 8?
We're
No.
done with all of them.
Are you gonna check them all on Monday?
Not necessarily on Monday.
Yeah.
Guys, have a happy Thanksgiving. Get those papers signed. Work on your homework through the rest of the unit, and you can start your fluids study.
Yeah, really, right?
Okay, do you know how many other like things we have? We're gonna have
So, how do you think you remedy that? So, what if you mean like a flashcard? And diagram, situation, some kind of like study cards. That's your Achilles heel. Then you need to protect that and work on that. Alright, so think about it. That's one suggestion. Think about what you're gonna do to take that on, because you either gotta step up or take a beating. And I don't want to see you take a beating. You know what I'm saying? Do you have any free? Do you want to meet together? Every day? Alright, so I'm free 8 every other day. Like that. So, like, do you understand how to do it?
We're gonna start fire today, apparently. What?
Do you want to meet today or the last one?
We're gonna make fire today, I think.
Alright. Remind me.
It was nice for you to show this. Huh? It's nice for you to show.
Good thing. So what did they talk about eating? I know.
Watch, there's some water on the floor over here. I gotta wipe it off. So you know that fire drill this morning?
Yeah.
You know who you can thank for that?
Oh yeah, it was his fire.
Tell her the funniest.
No.
The funniest thing just happened.
Why is it water?
Alright, Helena.
Water bottle. And she turned around and was like,
It's really the bow. Kool-Aid, really? Or we can go into class at
I'm getting it. I'm scheduling for it. Please. I'm getting it. My mom's scheduled it. I'm getting it at the end of December.
Be Carly. Carly needs it more than me.
Are you ready to mix it?
Bobby is
Good, yes? I am. Okay.
Find a staple, Taylor. Let's go to the garbage. Not a staple.
Can I use this?
tight curls.
Right here, right here.
How fun is it?
Why don't you do
Chris, what do you got?
Sorry, go out and buy it.
Yeah, can you pull it off yet?
Well, thank me. I will put it there. Yeah, you missed the ass. Put it there. All right, ladies and gentlemen, welcome to the challenge. Who will take the challenge? Freddie, can you open that window, please? What was your question, Corey? I did not.
Does it work?
Who would like to go first? Come on, Kevin. Wait a second. Where's Adam? Adam was outside. I was passed out from trying it.